Hi, everyone. Welcome back to AP Physics. Again, this is the topic that we're actually going to dive into our first topic that's common to both Physics B and C, hence topic BC1. Today we're going to be talking about the topic of kinematics. What's kinematics? It's really the fundamental concept in physics. Kine, or kin in Greek, means motion, and matics, like mathematics, means what? The study of. So really, kinematics, as we know, is the study of motion, or very, very simple motions, right? This is what got people interested in physics, is why certain things move, or how it moves, right? If I launch my chalk, how is it going to move? Where is it going to be? How far is it going to be? How high it's going to reach? And questions like that, or where is it going to be at a certain particular time, right? So motion has really got people interested in physics in the first place. So naturally, this is the first topic we are going to discuss. I'm going to divide kinematics in a couple parts. We're going to discuss the basics today. Going to talk about concepts. And in the subsequent topics, we're going to talk about expand the one-dimensional motion to two-dimensional and to see some applications of motion. Right? So let's dive right into it. So what is the most fundamental concept of motion? It's a concept of change, right? A change of what? Change of location, right? If I'm standing here, there's no motion, or there's a certain type of motion that we're not really interested in because I'm at rest. When I move my location, I automatically created motion through the process. When we talk about this, I like to bring up two things. One is that we're going to look at the kind of the scalar version, or the version that we're used to, or we talk about on a day-to-day basis, and we're going to talk about the vector version of that, which is what we are actually interested. Okay? So the most basic concept, you think about it, in scalar quantity, when we talk about moving, you say, how far did you move, right? Is the concept of distance. Right? We're all familiar with that, right? Distance, you know, how far you've gone, 2 meters, 3 meters. And we, in the first topic, in the previous topic we discussed, that's not a really good way to describe motion. Because if I say you moved a meter or moved a mile, it's not very descriptive because I can't find you, right? What's the vector version of a distance? Well, the vector version of distance is change of displacement. Or I like to call it delta S, change of displacement. In other words, displacement is basically your location, right? Your final location minus your initial location. Okay? So if you start off here and you end up here, this vector is your displacement, right? The magnitude part of this is the distance, right? And if you add the directional part, you will get the actual change of displacement. So change of displacement, it simply means change of location. Okay? Change of location. Now, if you think about it, change of location is the most basic way of motion. You moved, in our sense, by having a change of displacement, right? You go from this point to that point, you change your location, you created a motion, right? Distance kind of describes the same thing, but distance only tells you, oh yeah, you moved a mile. But again, that mile could be what? Anywhere. It's not very descriptive, right? But if I know where you started, where you end up from, I know exactly what your net change of position is. Here's the biggest difference between vector and scalar, and why we like to use vector to talk about change. So if I end up here, if I start off here, right, I end up there. Let's say the straight line distance between them is 1. So my change of displacement, if I go from here to there, is what? Going to be 1, right? So my delta S is 1 in this case. My distance is not necessarily 1. You say, Lynn, why is that? Because it depends on how I travel. Because if I end up doing this and then that, right? Let's say 1 and 1. My distance I travel going from this point to this point is actually what? 2, right? So the distance is actually different, okay? Or I can just do this, right? End up at the same spot. And in that case, my distance in this case, let's say 10, right? My distance is 10. What is my displacement? My displacement is still 1, right? I can go around and come back here, 20. My distance is literally how far I've gone. It's 20. But my displacement, my change of location, is still 1. Do you guys start to see the advantage of using this change of displacement concept or this vector concept? Why? Because it's consistent. I don't care how you get there. I just want to know where you start, right? Where you end up. Okay? It simplifies a lot of things, right? Because this, in essence, becomes path independent. It doesn't matter how I travel. It simplifies a lot of things. In physics, it doesn't matter how you get there. When you talk about kinematics, it matters is the only thing that matters is where you're from, where you started, to what? Where you end up with. That is the elegance of using vectors, because that's a very simple concept. For every single of these paths, my distance is going to vary, but my displacement, since I'm only counting the net difference between starting and ending position, sorry, this is an F, ending position, this is going to be my displacement. It's always going to be 1. Okay? That's why physicists prefer to use the concept of vector, or in this case, concept of displacement, over scalar quantities. Because it's uniform, it's consistent, and it's simple. So as you can see, physicists don't use vectors to torture students, right? Because it's actually meaningful, right? It makes sense. Why do I care how you get there? I just want to know where you started, where you end up with. Okay? In an elegant, simple universe, that's what matters. In physics, a lot of things are ideal, and this is an ideal case, right? I don't care how you get there. All I care about is where you start, where you end, and that's it. Okay? So this is the concept of displacement. It really simplifies a lot of things, right? Then the change is one thing. Then what I'm interested in is the rate of change, or in this case, speed. Right? We hear this term thrown around a lot. What's the speed? Right? What's your speed? It's how quickly did you get there? Right? If you travel the same mile within 10 minutes, it's okay. But if you travel the same mile in 20 minutes, you're kind of slow. If you travel the same mile in a minute, you're fast, right? This concept of speed, or fast or slow, is built in a scalar quantity, right? And we know speed is what? Just distance divided by time, right? We have the equivalent concept of vector, and a concept is called velocity, or average velocity, in this case for Physics B students. Okay? Velocity, or average velocity, is simply change of displacement over time, right? So if you think about this is analogous, this is also analogous, change of displacement over time. Okay? So let's see how does that work. Again, let's say I start off here. Right? I walked around a block. It's a 1-by-1 block. Right? And the whole trip, it took me 4 minutes. Okay? What is my, let's see, what is my speed? Your speed is going to be what? Your distance. How far you travel? 1, 2, 3, 4. 4, let's say, meters. Right? It will be 4 meters divided by 4 minutes, so 1 meter per minute. Okay? That is your speed. What is your velocity? Think about it. Your velocity in this case is what? 0. Why? Because you start off here, you end up here, so your change of displacement, or this concept of change of displacement, delta S, your starting location overlaps your ending location. Your change of displacement in this case is 0. You did not move. So if that's 0, your V is going to be what? Your average velocity, right? That bar means average velocity. Your average velocity is 0 because you didn't do anything. See, physics has a very cynical way of looking at things. If you end up where you're from, Why bother? You didn't do anything. You didn't, because there's a lack of motion as far as a vector sense is concerned, you did not move, right? Or your movement doesn't result in anything else, right? So you end up here, your delta S is going to be 0, and then 0 divided by whatever time. It takes you 10 hours, 20 hours, doesn't matter, you end up getting 0. Okay? So this is the difference between vectors and speed, and keep that in mind. And I know we're all familiar with the scalar quantities, and we like to use scalar quantities, but from now on, we have to switch. We have to get used to how vectors are dealt with. Okay? And especially, this concept of displacement is very, very important. So far, you know, not bad, right? Now, but we all know, we don't just travel at a constant speed, right? When you drive, you start off 0, right, whatever it is, and then you hit the gas, you speed up, right? The concept of speed up implies what? Your speed changes. You don't always just go at a constant speed. So when you have a change of speed, we have a term to describe it, it's not really accurate. People use the term acceleration, but that's not really a scalar quantity. Acceleration or average acceleration is defined as v final minus v initial divided by t, or delta v over t. Change of velocity over time. What was your velocity to begin with? What was your velocity at the end of a motion? Okay? So these are the 3 fundamental concepts of kinematics, 3 fundamental units of kinematics that you have to know. Let's take a look at their units. Now we're on the topic. What is the change of displacement? The standard unit is meter. That's because all physicists use meters. They call them the SI units. If you remember chemistry, that's what people use, right? Displacement over time, meters per second, and that's the change, that's the velocity unit, right? So this is velocity over time, so its acceleration is meters squared over second. Okay, so that's what the concepts are. So the 3 fundamental changes, right? 3 fundamental change of location, and with that, you can change the location either with velocity, right, divided by t. You get the average rate of change, right? And with acceleration, you'll see that your velocity actually changes, and then you'll see how that works. So this is more of a conceptual way or basic way of looking at this. For both physics B and physics C, that's how you look at things, right? Mathematically, physics B and physics C has different way of dealing with this. In physics, this is how physics B would deal with this, just with arithmetic. Physics C will kind of employ calculus. And then when we're dealing with physics C, we'll talk about specifically how do we do that with calculus, okay? But right now, we're just focusing on the concepts. So now we have this whole concept of vector quantities, right? How are they related? There are really 2 types of motions that I'm interested. What are types of motions? Are really the 2 types of motions that you're going to be dealing with in your physics course. The first type is constant velocity motion. Very boring, right? Your velocity doesn't change. You're going at a meter per second, you're always going a meter per second. Kind of like a steady state, right? We don't encounter these motions a lot because, come on, you got to start somewhere, right? But in the case of a constant velocity motion, you have what? The only governing equation is this guy, right? Your velocity, it changes the displacement over time. So if I know any of the 2 concepts, okay, I can figure out the next one, right? If I know you're moving at 2 meters per second in one direction, right, and move that for 10 seconds, your displacement is what? 20. That's it. Now, assume you didn't change direction. And we don't assume that, okay? Always assume straight line motion until the next part. Right, that's it. That's all you need to know. So very simple, very idealized motion, right? Straightforward, straight line, constant velocity. We're going to discover kind of like discover one motion that's just simple constant velocity. What's the second type? The second type is slightly more interesting. The second type is slightly more complicated. It's constant acceleration. Okay? Constant acceleration. So in that case, it's a little bit more, right? It implies if you have an acceleration, that means what? This a is not equal to 0, right? Or your average acceleration is not equal to 0, but it's constant. Your acceleration doesn't change. That means, for an example, if you're driving, that means your force on the gas remains constant. Okay? It doesn't change, right? So constant acceleration motion, of course, is governed by this equation, a v final minus v initial divided by t, right? V final minus. So if you know the final velocity, if you know the initial velocity, you know the time, you can calculate acceleration. Or if you know any of the three concepts, you can calculate the other one, right? There are two more equations I want you to know, and you need to know that, okay? So what about, I want to work displacement into this, right? You can substitute v final, v initial with this equation, right? And you can kind of figure out and juggle around. You get the two equations. I'm going to actually not going to show you how to derive these, but just put them on the board. If you remember, you definitely remember them if you take high school physics. The first one is what? Displacement is equal to the initial velocity times time plus 1/2 at squared. How far you have traveled is equal to the initial velocity that you have times the time you travel plus 1/2 of acceleration times time squared. Okay, that's one. Second one, v final square is equal to v initial square plus 2a delta s. Okay? 2a delta s. This implies what? Your final velocity squared is equal to your initial velocity squared plus 2a times the change of displacement. Right? Does it work? Of course. Right? Of course it does. So, these are the three equations that you need to master if I tell you a particular motion is at constant acceleration. Let's take a look at an example. And I'll show you how I solve all these kinematics problems. A car is moving at 10 meters per second, right? And if I hit the gas, I want to go faster. If I end up accelerating 2 meters per second squared for 2 seconds, how far have I gone? Have I traveled in a car? Okay, how far have I traveled in a car? This is how I would do it, right? The way I would do any physics problem, I would list what I know. Look at the question. The car is traveling 10 meters per second, right? What is that? That's your initial velocity. So I know VI is equal to 10 meters per second, right? This helps you kind of narrow down things a little bit. And accelerating, and hit the gas, and it's accelerating at 2 meters per second squared. So A is 2 meters per second squared, right? For 2 seconds. I know what, in that case, T is equal to 2 seconds, right? Always have the unit next to it, too. How far have I traveled? What am I asking? I'm asking what? How far, in a sense, this is what? Displacement. Right? And if you remember the equations, you say, all right, I know VI, I know A, I know T, VI, T, and A. Oh, I'm going to use the second equation. There you go. Displacement, always write down what equation you're using. Very helpful, good discipline. VI times T plus 1/2 AT squared. Second step, substitute the quantities in. See if the units work out. Right? I'm going to do this here. 10 meters per second times 2 seconds plus 1/2 times 2 meters per second squared times 2 seconds squared. Just do it for now. Then later on, I will skip the unit. Just make the problem a little bit simpler. All right, just want to show you how the units work out. You got 20 meters plus, this is 4 seconds squared, right? Second square cancels out second square. That cancels out, becomes 1. So there's simply 4 meters and 24 meters. That's it. When you're done, box the answer and you're good. On the short answer part of the AP exam, this is what you're supposed to do. List the knowns, list the unknowns, have an equation, substitute it in, have the final answer, box it, and you're done. If you do it this way, your exam grader will love you, and you'll get all the credit you need. Okay? Another way, kind of why I like to write out all the steps, is in case you make a mistake, they can find out what the mistake is and give you partial credit for the ones that you got right. So if you made a last-minute mistake, you say, oh, that's 25. You know what? You probably get majority of the credit, and that's how college works. Okay? They don't necessarily care what the final answer is. People care about your thinking process, if you are logical, right? If you can think straight, and also how you derive the answer. The answer itself is trivial, right? Yeah, you probably get full credit if you get the answer right, but if you don't, you lose a point or so. Not a big deal, okay? You need to actually have this discipline built in when you solve physics problems, okay? List the knowns, list the unknowns, list the equation you're using, why you're using it, pop the numbers in, and you're done. Numbers are the least important part, okay? It's the conceptual part that's interesting. Let's do one more. So, I'm driving, right? Second example. I'm driving. I'm driving at, again, let's say 20 meters per second. I'm just casually driving. All right, and I see a traffic stop in front of me. All right. So I hit the gas. Oh, well, not hit the gas. I hit the brake. I know my car can decelerate at 2 meters per second squared. What is the minimal distance displacement I need for my car to come to a full stop? Right? Because you know if you hit the gas, hit the stop, hit the brake, your car's just not going to stop right away. Right? It takes some time. What is that minimal distance for me to stop? Because if it passes the traffic light, I'm pretty much screwed. I'll get a ticket. Right? Think about it. So again, use the same approach. List what you know. What do I know? I was going at 20 meters per second, so I know VI is 20 meters per second. I know my acceleration, in this case it's negative acceleration, or in other words, deceleration. I know my acceleration is negative 2 meters per second squared. What is the minimal displacement you need to have before you come to a full stop, right? What is the distance that you're going to skid? The cars are going to skid before you come to a full stop. Well, so I'm obviously looking for displacement. And you look at this, you're a little bit puzzled. You say, well, something's missing. Why? Because for any of these constant acceleration motion equations, you need to have 3 unknowns, right? 3 knowns. I only have 2, VI and A. And I'm looking for the fourth one. I don't have anything else. This is when physics come into play. You have to know what's implied. What is implied in this problem? You have to what? You're hitting the brake. You want to know when you stop, what is your distance? When you stop, what does that mean when you stop? That means your final velocity has to be what? 0. That is implied. They never tell you that. Well, I put a full stop there just to give you guys a hint, but they never tell you that in the problem. This is the part that's different between physics and a math problem. Physics, you have to think about in a real life situation or an ideal life situation, what's happening. What is implied in a problem that's not in a mathematical expression, right? There's no way you can solve this in a mathematical way because you don't know one piece of information, assuming you only do math, right? But from a physics point of view, you say, well, I need to come to a full stop. So what I need to have is what? My final velocity being equal to 0. Okay? But once you know that, bingo, you're done. You know VI, you know VF, you know A. Oh, you're looking for delta S. Bingo, you're done. List the question, list the expression. V final squared is equal to V initial squared plus 2A delta S. I'm going to skip the units this time, but you know what to do. V final squared is 0, right? V initial is 20 squared plus 2 times A is negative 2 because I'm going the opposite direction, right? Times delta S. Delta is what I'm looking for. Oh, sorry, this is negative 2. Right? So here I get 0 is equal to 400 minus 4 delta S. Move this around, divided by it, delta S is equal to 100 meters. So what that means is that you need to have 100 meters of distance before you completely stop. The car comes to a complete stop, right? If the traffic light is 80 meters away, that means you've gone in an intersection. That's not good, okay? So these are the questions that you need to know. I'm showing you this. Again, the math part is trivial, the equation part is trivial, but the point is, in physics, you are allowed to kind of stipulate, you're allowed to kind of tell yourself, this is implied. There's a lot of implied information that you need to get from a problem. This is no longer the mathematical way of solving things. This is a physics way of solving things. Physics has to relate to real life, and you know when you come to a full stop, this has to become zero. Okay? So this is really the fundamentals of what I like to call one-dimensional kinematics, right? We're only going to discuss two types of motions. Constant velocity, we didn't even deal with that because it's so easy, and constant acceleration. Practice, get some practice in, do some problems in the textbook, and be really familiar with these three things. I don't ask you guys to memorize a lot of things. You need to know these three. They're the fundamentals of physics, fundamentals of kinematics nonetheless, right? And that's it. That's all you know in kinematics. You don't have to know anything else.